Good morning or good evening, everyone. Welcome to another tutorial on structural dynamics. Today we look at a problem on forced vibration where the forcing function is of an impasse nature. So previously in tutorial number 2, we looked at when the forcing function is harmonic. You can watch that tutorial here. You click that link above on top here. So you'll be able to read more on that. Thank you for those people who've continued subscribing to this channel. If you're not subscribed, kindly click the subscription button and God bless you. Let's see the problem. So we are given this problem where we are told a reinforced concrete tank rests on 20-meter tall concrete column. Then a cable is attached to the tank, applies a lateral force of 8 newtons, and it displaces it horizontally 5 centimeters. So the cable now is suddenly cut, and the resulting free vibration. So these are the initial condition: initial displacement of 5 centimeters. Then there is a static force which is giving this displacement. Then once the cable is cut, free vibration ensues. So at the end of 4 cycles, the time is 2 seconds and the amplitude is 25 millimeter. And you see we started with 5. So it means there is a reduction in amplitude. What does that tell you? There is damping that is occurring. So you're required to calculate the damping ratio, the damping coefficient, the number of cycles required to bring displacement amplitude to about 5 millimeters. Now, if the water tank, when it's full, this is the second part. The first part is up to that point. Now, the second part, you're told the water tank is full. Now, it's subjected. So you see, the first part, we are just dealing with what we call the free vibration. All right? Free vibration, which is damped. So this one is like tutorial number 1. Yeah, that's when we tackled that. Those are the kind of expression we are going to use, the same that you use in that tutorial. So the second part, if the water tank, when full, is subjected to a dynamic impasse force. A dynamic impasse force, we talked about the different type of dynamic loading, and you can read our lesson number 1, lecture number 1. The link is up there. You can get to understand more on the different types of loading. And in dynamic force impasse, it's a force that will act on a very short time and then stop, like an impasse of a ball hits on a wall. So you are required now to determine the maximum shear at bending moment at the base of the tower, and you're also given the capacity of the tank is 40 meters cubed. So let's see. This is the impasse. This is the nature. So you see, it's only acting for 0.08 seconds. Yeah, so it's very short duration, pure impasse force. And you can see the magnitude decreases from 200 all the way until it comes to 0. So you can try to imagine like this is the typical of a ball hitting on a wall, or even a bomb. It's acts on a very small duration of time. That's an impasse. So let's see a typical solution. As always, I always say you can have different approaches, but what I'm trying to do in this, for those who have been following us in our lecture series, so I'm trying to follow the method that we have been following, and also I try to use the simplest and the most direct method to solve. So as always, I said first visualize your problem. So you are given initial displacement, 5 centimeters, and the final displacement, you are told after some period of time comes to 2.5 after 4 cycles. Then you're also given this is a force that is pulling the column backward. So this is a static force, and the static displacement is 5 centimeters. So to visualize, so we are saying is it's like a column there, 20. Remember, you're not told the height. There's some assumption now that you make here. We are not told what is the height of these. It's like it's not of our consideration. What is the height of the column itself, of the tank itself? So what you do here in this case, the first assumption, you can assume up to the center of the centroid of the tank. That is where we have 20. Okay, 20 meters, and then this is slightly displaced. So there is an initial displacement. So it's displaced by 5 centimeters. Another thing, that the force that is displacing, that is stretching this, the force of 80 kilonewton, the one I said is static. So 80 kilonewton force is stretching, it provides a displacement of 5 centimeters. So you see the column, something that I want now, even before you start solving this, because from the values that you're given, you should start visualizing what is this problem talking about. So with this static force giving this displacement, we can get the stiffness of the column, because we know F is equals to K times the static displacement. So this is Hooke's law. So you can be able to get the stiffness of the column. But let me not go ahead of myself. Let's go to our problems now. So you have, this is the first step. Always when you are given data, look at what you have. Then go ahead and start visualizing before you can, so that you can know what are the best equations or formulas that you need to use. So the first thing is you are told to evaluate the damping ratio. Now, as usual, the damping ratio, I know you know this, and if you go directly to our lecture number 3, I have shared that link there, so you can be able to move the lecture number 3. You can click the link here. You are going to see the damping ratio, what we call the xi, is given by C over C critical. I'm not going to explain this much because we talked about critically damped systems, over damped system, and the damped system. So you can see that when you click this link in in lecture number 3. And you see in my lecture, I have indicated the timestamp. When you go to the description on YouTube, if you want to go direct to a certain area, like in definition, like in an example, you just go to the timestamp and you click that time, and it will take you direct. You don't have to watch the whole video if you don't have much time. But now go there and understand about that. But you see now, from what you have been provided, now this is why I was saying, look at the data that you have. From what that have been provided, we do not have the damping coefficient, neither the critical damping coefficient. So it means this is the only information that we have been given. So what do we do now? So we have to look at other method, other approach. So recall again from the same lecture, lecture number 3, we are given that these are what we called the logarithmic decrement. Logarithmic decrement is something like this, and it's well explained in that lecture. So we have our motion. Then let's say it starts like that, then it goes on decreasing. So we said this decline is logarithmic, is exponential in nature. And so the amplitude, the first amplitude, you can call it U0 or U1, continue decreasing because of damping. And we said if you want to get the logarithmic decrement, the rate at which this decrement occurs, then you just need to get the natural log of U1 over U2, or any two consecutive amplitude. So you cannot take, this is U3, this is U3. You cannot take U1 divided by U3. If you say U1 divided by U3, you'll be talking of 2 cycles. So that will be 2 times that logarithmic decrement. So with that in mind, again, there are 2 expressions. This one of them. The second one is where now the logarithmic decrement was approximated using twice pi times. Now this is what we are looking for, the damping ratio, xi. So you see, already we know the amplitude changes with the different cycles. After 4 cycles, so if I just bring back my displacement, so you say 2, 3, 4. I hope my sketching is okay. So we have the U0 here, or U1, U2, U3, U4 is equals to the amplitude here is 5, is reduced up to 2.5 after 4 cycles. So note that we can also express these 4 cycles, U0 over U4, is the dot product, U0 divided by U1, U1, U2, U2, U3, U3, U4. You see, like if this one goes cancelling like this, we are left with U0 over U4. So you can, it's a dot product of, note that we have dot product and cross product. This dot product of the different ratios of the amplitude, a consecutive amplitudes. Now with this, if you put, now remember the logarithmic decrement, we now use the we introduce the natural logarithm. So if you introduce the natural log, this one will be U0 over U4. For each one of these, remember the multiplication of numbers is addition of their logs. So it means this one U0 over U1, this is the same as if you put log U0 log into bracket U0 over U1, that will give you the first logarithmic decrement. Remember I said logarithmic decrement is just the natural log of any two ratios, consecutive ratios. So this one will be one, another logarithmic decrement, another, and another. This is what we are putting here. This one, of course, the natural will remain here because U0 over U4, they are not consecutive. Now this one becomes 4 logarithmic decrement, or if you add them, it becomes 4 delta. So in short, we can now factor in our values, the amplitude at the first cycle and the amplitude at the fourth amplitude. So you're going to get the logarithmic decrement as 0.173. And now you see, once you have this, you can be able to use this second formula here. And you are going to obtain what is the damping ratio as 2.76. So you see, based on the data that you are given, you should now be able to know which is the best approach or formula that we should be able to use. The first and the most direct is not always the most convenient or suitable for solving the problem. It's based with what information you have in your question. But number 2, the damping coefficient. So the damping coefficient, C, is given by this equation. Again, just go to that lecture number 2. Is it 2? No, lecture number 3. You'll be able to see this expression. So we have, okay, you see now the stiffness is required here. And I said from the information you're given the static force, static displacement, you can be able to get the stiffness. The mass. So remember the natural, the circular frequency is given by the root of stiffness divided by the mass. So we can be able now to make m the subject of the formula. And again, now this is all based with the information that we have from the question. So the natural frequency is given by 2 pi. Remember, this is just a rearrangement because I know you know it in this format, that the period is equals to 2 pi over omega. This is the relationship between the period and the amplitude. And this is in lesson number 2. So we can be able now to make omega the subject of the formula. We get the value as 12.57. Remember, where did we get this? Where did we get the period from as 2 over 4? If you look at that question very quickly, you should be able to realize that we are given at the end of 4 cycles, the time is 2 seconds. So, and remember, a period is the time, even without drawing that. A period is time for 1 cycle. So if for 4 cycles the period is 2 seconds, what is for 1 cycle? That's why you are saying is 2 divided by 4, 0.5 seconds. So with that, we have been able to get the frequency, the circular frequency, and then we have the stiffness. So you just need to plug in the values. You get the mass as 10.132. So you see, the mass of the water tank on top we are not given, but now we have been able to work backwards from the values that we have to be able to obtain what is the mass, what is the lumped mass. Remember, in our dynamic analysis, we said the mass will be lumped, say at the floor levels. The columns only provide the stiffness. So this is the mass, lumped mass here of the water tank is the one that we have calculated to be 10 tons. So now we can go there. This was like a side calculation. You can see I have done an indent. This is how you arrange your work. It becomes very clear. Some part you put them into, okay, I'm not saying you can use all those brackets, but the organization, because this is like the primary level, we are calculating the damping coefficient, but the other things from the formula we are using, the other things that we need to calculate. I always fight the student to trying to do the working in an exam. They are doing this working at the back of the page, or they use a pencil, then they cancel. No. This is part of your working, but just arrange it so that it's easy to follow and flow. Because if I don't see this working, remember I'm awarding marks here. There is a mark for that part, a mark for that, and a mark for that. When you erase, or when you put at the back, or when you cancel, I can't mark it. Okay. So, and as I said, the method is very important. Method is important, even more than the final answer. You might have a problem punching the calculator here, but I might not penalize you much if I can see the workings is okay. Then, so the other part now is on just to plug in the values. We have what is the our damping ratio, xi. We have stiffness, we have the mass. You just plug in, you get the answer as 7023. This is the damping coefficient. Now part 3. The number of cycles for our displacement amplitude to decrease to 0.5. So remember we started with 5. This is just, I'm going quickly because this one we had it in the previous slide. We said between U0 to UN at the end of the cycle, we find dot product of those ratios, and when you introduce the natural log, we are saying it's just a summation of the different damping logarithmic decrement values. So if there are n cycles U0 of a UN, you have n times delta. So what you want to know is that how many cycles. So 5, we want to get how many cycles do we need to get to 0.5. This will be the same as we have calculated the logarithmic decrement in the previous slide as 0.73 n. So this is the n we want to get, and this is just about 13 cycles. Very simple. So let's go to the second part of our question, and here now maybe I might put a line there, because whatever we are calculating was based on lecture number 2 and 3. Now this is now based on lecture number 5. This way we come to impulse load, and we are going to see something what we call the Duhamel's integral. So lesson number 5, you can click the link here. The link will appear here. You can read that summary of the integrals that we need to use. So from that lesson, the response, now this is the displacement response due to a pure impulse load, is given by this expression. This is the integration of the impulse loading, and you can see I'm saying delta tau because this very small time interval, you have something like this. You may find like this is the t, our motion will continue after the impact. You know, when you hit the structure, the motion will continue, maybe at the free vibration. So the time will continue. There's a time, this is the time we are calling tau, between 0, when just very small time, when the impact or the impulse is acting, 0 to tau, that's the integration of that part. So this is the dynamic response. This is the response because or just when this force is acting. So if you want to get the overall, you have to add. You need to add now the continuing motion. If I say at the time t is equals to 1 second, remember this add up to 0.08 second. That's what we found from our question. So if I want to see what is the response, what will be the displacement after 1 second, so it means there's another motion that I have to add. Now I have to add free vibration that is occurring. Okay, but for our case here, we just want to know what, or the question is asking for maximum base shear and bending moment at the base due to the dynamic force, the impulse. So the question here, I just want to see whether you can be able to evaluate the Duhamel or Duhamel integral just when this force is acting. All right. So let me just erase this to create more working space. So what we just need to do is to work out this integral between 0 and 0.08 seconds. So the mass, now the tank is full, and we are told when it's full. So this is the secondary information that we are given. So it means the mass we have calculated before, we never calculated for the content that is inside. But if the tank was full initially, and we are given that the displacement, we are given the static force that provide that displacement, if that occurred when there was water or the tank was full, then we would have gotten the mass earlier on. But this information is given later on. It means this water, initially the water tank was empty. So 40 meters cubed, this is about 40,000 liters or 40,000 kilograms. So you just need to add to the mass of the empty water tank to the mass of the water. You get that as the overall mass. Then the other thing we need to get is this, the frequency, circular frequency. Why does it change? Because again, the frequency, even the natural period of the water tank when it's empty is different from it's full, because these things, they depend with the mass. So again, the formula is the same. So only what changes now is the mass. Our mass here now is including the mass of the water, and we get the angular frequency at 5.65 runs per second. So this one I have just now compressed it very clear because I want everything to fit in this slide. So this part, you have it, the mass 5132, you have the frequency. Then here, this dual integral, how to evaluate it numerically, I just use the trapezoidal rule. So the trapezoidal rule, you had this. I want to just place this one, everything here. You had the time interval is 0.2. Then you have this is 200 kilonewton. Then we come to 80. Then we have 20. And then we have 0. And the starting was 0. So you know the trapezoidal rule, the time interval over 2, 0, then twice the second part, twice the third ordinate, twice the fourth ordinate, then the last ordinate. Again, this is in kilonewton. So remember, we are dealing with the newtons, so that's why I multiplied by 10 to the power of 3. So you work that out one. So kindly place your calculator so that you can confirm that the answer is 0.0212 meters or 21 millimeters. That is the displacement due to that impasse after 0.08 seconds. So again, now we have the displacement, we have the stiffness. So you can be able to get the static force with the water tank when it's full. And that one, you just plug in the value, get it at 3.9 kilonewton. And that is the shear force. The shear force, of course, is that static force that we have calculated. And of course, our bedding moment. Remember the water tank, this is fixed. The mass is lumped here, so it's a cantilever. Okay. So the displacement is like that. So the bedding moment is just the force applied at this part times this distance, the height, which is 20. So, and now you can sketch your bedding moment, the shear force and the bedding moment diagram. So first you sketch your tank there. Okay, this is the best way to sketch this. They have to be the same height. It's better to keep them the same height. So the shear force is just that value. This is 33.9. Okay, this is the tank. Then this is the shear force. Okay. Then the bedding moment is something like that. Okay. So this will be the maximum bedding moment, 678 kilonewton meter. Here it will be 0 at the top. So these are the shear force and the bedding moment diagram, and that marks the end of our tutorial. That tutorial have spent over almost 25 minutes, but I wanted to explain the last part clearly. So, and again, that marks the end of our tutorial for the continuous assessment that I have given to my class. But there are questions that have been coming up. Like now, Mr. Dan Owen asked a question on on earthquake, where you're using the spectral analysis in my email, and I felt that if I have time I can make that tutorial. So this is not the end of my tutorials, and also the videos I keep on uploading. Wait or check out for the next tutorial. When I get time I can upload. So keep watching, keep subscribing, keep liking, keep sharing, keep commenting, and let me know where you have not understood so that we can explain further. Thank you. God bless you. See you in the next learning session. Bye bye.